That makes a lot of sense.
Yeah, that's right.
Okay, so we left off on this yesterday, right? Let's just kind of review the problem. This one is topical, to say the least, here with our weather. So you're driving this car, driving at constant speed along straight icy roads, slam on the brakes, wheels lock, so we're sliding on the ice, and you slide a distance of 40.8 meters. The coefficient of kinetic friction is what? That's what we're trying to find. Okay, so there's some old and some new here, right? Turns out there's going to be some kinematics, right? We'll never get away from the kinematics. That's always a big part of what we do. So we're going to have to use the kinematics to determine what the acceleration is, right? But then we also need to know what's going on with the forces. So we needed a free body diagram. And if the car is traveling to the right, everybody agree that the vertical forces offset. We got the weight down, normal force up. And there's only one horizontal force, which is the slowing force, the braking force, right? The friction is pushing against us to slow us down, right? And so our equations of motion then, we end up getting our vertical net force is just going to be this positive one plus that negative one. So normal force minus mg is 0 because there's no vertical acceleration. That's useful because that tells us that normal force is just equal to weight, okay? Horizontally, the net force was the only one force acting, which was kinetic friction. We know that kinetic friction is equal to mu sub k times normal force, but normal force is mg, right? So we come up with, and why is that negative, by the way? It's going in the negative direction, right? Okay, so then we get negative mu sub k times mg equals net force is just ma, right? And so for us to solve for mu sub k, we've got to know what acceleration is going to be. Because really, what we're going to end up getting, if we isolate mu algebraically here, let's see what happens. If I isolate mu, what am I left with? I already divided both sides by m and got rid of those. But what am I going to do to get the mu by itself? Divide by g, and then what about that negative side? Multiply or divide by a negative, right? Everybody agree? And so it's just going to be the ratio of acceleration divided by acceleration of gravity. That's it, okay? But we got to know acceleration, right? And so that's where we sort of left off then. We had to turn this into a kinematics problem. We know that our initial velocity is 11.2. Final velocity is 0 because we're coming to rest. The displacement is positive 40.8, right? And we're trying to find acceleration, and that's just equation number 4, right? And so that's where we left off. That's the equation we want. Let's plug in our values. So we get final velocity, so we get 0 minus 11.2 squared equals 2a times, what do we get? 40.8 standard units, right? So if I'm solving for a, all I've got to do is just divide negative 11.2 squared by 2 times 40.8. Everybody agree? To get that a by itself, just divide all that stuff away, both sides. And that's just a calculator problem. So what does that give us? Okay, so negative 11.2 squared divided by the quantity 2 times 40.8 is that number, negative 1.54-ish, right? That's a calculator number. We'll leave it in there. But we can just use it because really our coefficient of friction is just negative a over g, right? So we'll just take that number times negative 1 So I think I can even go negative answer, okay? Look at my double negatives, divided by 9.8 is that, okay? How many sig figs do we get to keep? I'm thinking 3 it looks like. So rounded to 3 places, what do we get? 0.157 would be our answer. Okay, what are the units of that? The coefficient? Ah, good, trick question. They're unitless. No units, good. Okay, good. And then the last one, I thought this was a real good one to take a look at. You guys want to do some algebra 2? Nah.
So I just want to double check on the action-reaction pairs.
Mm-hmm.
Those have to be two opposite things that are equal, acting on the same thing.
Yeah, they have to act between two objects.
Right.
Right?
It was the same
So,
thing.
right, so
Gravitational.
exactly, right. So it'd be like Earth on cup on Earth. Okay? And those would both be gravitational.
But like this would be Earth's mass on the water, or gravitation on the water bottle, and then the normal force.
Okay, so before we jump to this next one, it's a good question. So let's take the example of my coffee cup sitting on the table, right? So somebody name an action-reaction pair that's at play here.
Coffee on the table on the coffee.
Okay, good. So there's the normal force of the surface force, or the normal force. Table pushes on coffee cup pushes on table, right? So there's one. What's another one? Ah, there you go. So the mass of the Earth pulls on the coffee cup gravitationally, and therefore the reaction force must be, okay, the coffee cup pulls on the Earth gravitationally, right? Make sense? Okay? Okay, so I think, I can't remember where that one is. Abby, that was the one with this one, I think, right?
Yep.
That one?
Yeah.
Okay, good.
And didn't you say you were going to clear all the previous attempts from the first test?
Yes, I will.
Okay.
Yep. Okay, let's have a quick look at this one. Okay, free body diagram. What do we got here? Braden, help us out. What do we got going?
Attention.
Okay, good. So we're pulling on a sled across flat, snow-covered ground. So we've got a tension force pulling to the right, let's say. Okay, what else? Friction acting in which direction? Left. Kinetic friction. Okay, what else is going on? Okay, gravity's pulling it down. And normal force vertically upward, okay? All right, so it wants to know a force of more than blank will be required to start the sled moving. So the sled isn't moving yet, right? So what kind of friction is actually acting in part one? Static friction. So that needs to be an S instead of a K, right? Am I recording this? Yes, I am. Good. Okay. So then we're gonna set up our our equations of motion are starting to look pretty similar each time, aren't they? And that's gonna happen with situations like this. They're all gonna be pretty similar. What's gonna be the vertical equation of motion? What's the net force gonna consist of? Normal force is positive. plus negative mg, so minus mg equals 0. So that tells us that normal force in this case equals what? Equals weight. Makes sense, right? From our picture, we can see that those are the only vertical forces acting and they're in equilibrium, right? Okay, equation 2. What's happening horizontally in this case then? In this part right here, so if we're just gonna break the sled free, let's pretend that we haven't quite broken it free. We're increasing and increasing and increasing the tension, but it hasn't quite broken free yet. What's going on then? What's the net force? What? Tension is pulling in the positive direction, minus static friction, I guess, equals what? Is it actually accelerating? No, it's not, is it? When we're just breaking it free, we're just getting to the point where we're going to overcome that static friction that's preventing it from accelerating, right? So this too is actually equal to 0, right? Does that make sense? Okay. Now, quick review. It's been a while. If I've got this object on the table, and I push with 1 Newton of force, and as a physicist, I can tightly control that's exactly 1 Newton of force I'm pushing. Believe that. Okay, so I'm pushing with 1 Newton. What's the static frictional force resisting me? Higher than 1 Newton? Everybody say?
Yep.
Okay, if it's higher than 1 Newton, what's going to happen when I push to the right on this thing? It's going to slide the opposite direction at me. That's not going to happen, is it? Right?
You never know.
But
Have you tried it?
yeah, I'm pushing now, and it's not coming towards me.
I'm sure there's a slim.
Okay, so that really wouldn't make sense, would it? The static frictional force is not, if I press with 1 Newton, it's not going to press with 2 Newtons against me. What's it going to do?
Normalize it out.
It's going to resist me as long as it can, isn't it? So if I push with 1 Newton, what's the return force going to be? 1 Newton. If I push with 2, it's going to be 2. But if I surpass that threshold and I push with more force than it can resist me with, it's going to break free and start sliding. Agreed? Okay, so then that's why when we write this equation out, it looks a little goofy. The static frictional force is just greater than 0, but less than or equal to the maximum that it can provide, right? It's always going to it's going to smoothly adjust that up to the most that it can resist with, and then we break it free. Okay, so then this just tells us that the tension force has to be equal to the maximum static frictional force, right? Okay, so must equal static frictional force, which is from our equation, the maximum static frictional force is just mu sub s times normal force, but what's normal force? Mg, right? Does that make sense? So that's the tension we have to pull with. Whatever 0.259 times 49.72 times 9.8, whatever that gives me, okay, is the answer to part 1. Agreed? Okay, so Nathan, what about part 2? Questions on part 1, does that make sense? We okay with that? Okay, give me a 1 to 5. 5 means, yeah, Mr. Ryan, move out, we got it, move on. 1 means, that makes no sense. Flash me a little physics sign here. All right, okay. All right. Okay, all right. So Nathan, what about part 2? Now we're switching to a little different situation here. A force of at least blank will be required to keep the sled moving at a constant velocity of, who cares? All we care about is that it's constant velocity. So what's the only difference in our free body diagram when we move to part 2? Well, actually, maybe it's even okay the way it is. What do you think? Say it again. Sled's moving. Good. Is there a net force? There's not, is there? Right? Because it's constant velocity, so there's 0 acceleration. So the only difference is instead of an S, that becomes a K, right? But it's really the same thing as before. The math all looks exactly the same, with the one exception. I just have to change that to a K. Oops. right? And so then the tension now would just be the kinetic frictional force, which is 0.171, slightly less, right? 0.171 times m times 9.8, right? A little less force is required to slide the sled at constant speed than to break it free, right? Remember, that's how anti-lock brakes work. And then finally, the last one would be a force of blank must be applied to the sled to accelerate it at 3.11 meters per second squared. Okay, that changes things once again. What does that do to our second equation of motion here? The net force is now equal to what? Not zero, because it's actually accelerated. So what would it equal? Yeah, ma, right? So we get, for part three, whoops. For part three, we're gonna get ma, right? And so now when we solve for tension, it equals ma plus that kinetic frictional force, right? So ma plus mu sub k mg, right? So it's the same answer as part two, plus m, so 49.72 times 3.11, right? We've got a certain amount of force to keep it moving at constant speed to overcome the kinetic friction, and some more force required to provide that additional acceleration. Okay? Make sense? All right. Have at it. Test away. I'll delete some attempts.